All right, so this video is going to go over pages 7 through 9 in your packet, in your forces packet. So we're going to start talking about free body diagrams. So free body diagrams is basically just a basic drawing telling you what forces are there and which direction they're acting. So we're going to go over the 7 types. So the first one we're going to look at is applied force. So if you notice that little A subscript, okay, well, that basically means applied. Okay, so when you label something, you don't have to write out applied force, just write FA. So if I were to drawing an arrow, I would just say FA. Okay, so whichever way it's going, you just label it FA. So description of that, it is the force applied to an object by a person or another object. So example could be something like pushing a desk, pulling a rope. Okay, so applied force is not too difficult to understand. It's just whatever force you're applying to an object, either you are or another object is. Like if a train hits a car and stuff like that, that train would be exerting an applied force on that car. So that is your first type. So next one is going to be gravitational force or gravity force. So that's going to be characterized by Fg. Okay, that is also known as weight. Okay, so weight is actually your mass times gravity. Okay, so which is in newtons. Okay, now you're not going to see it in newtons on your scale and stuff. It's been converted to pounds in that case. Okay, but gravity force is the weight of an object. Okay, so big thing here is Fg is always directed downward. Okay, so it's always pointing down, so I would label this arrow right here Fg. Okay, and if you want to find the force of gravity, it is simply mass times gravity. Okay, so if I gave you a force and I ask you to find the mass of this object, okay, all you got to do is divide by gravity and you can find the mass. Now your units for this is mass will be in kilograms. So remember, it has to be in kilograms, so if 1 kilogram equals 1,000 grams, so if I give you something in grams, you're going to divide by 1,000 to fix that. Okay, so if you're wondering on which one you should do, if you multiply, let's say I had 100 grams and I asked you to convert that to kilograms, and you convert that by multiplying, now you're telling me I have 100,000 kilograms. That really probably shouldn't make sense. Okay, so grams are smaller, so divide by 1,000, then I'll fix it. And your gravity is still going to be 9.8 meters per second squared. That's not changing. So the force of gravity is going to be weight, which is basically what it is, which is also in newtons. So if I give you something like it has a weight of 18 newtons, that is the force of gravity. That is your Fg. Now your normal force is basically the opposite, okay, if there's a surface involved. Okay, so if you're setting something on a surface, so say this is like a book on a table, okay, you have Fg that's pulling it down and it's pushing on that table, but that table is actually exerting a force right back. Okay, so if you think about that is if you take your hand and put it on the table right now, okay, if there wasn't a normal force pushing back, you'd be going through the table. Okay, so there's this table kind of pushing back against your force. So it's known as a support force exerted on an object in contact with another stable object. So normal force won't always be there. If you have something that's like falling in the air and stuff like that, there's no other surface that's in contact with, so normal force wouldn't be there. So normal force is only there if there's another surface pushing back. So your example would be like a book on a table. That table is pushing down on that book is pushing down the table because of the force of gravity, and that table is pushing back with a normal force, okay, to basically support that book. Now your frictional force, that is exerted by a surface as an object moves across it or tries to. Okay, so just because you're trying to move doesn't mean you're necessarily always going to, because if the frictional value is high enough, it will keep you from doing so. Okay, so like you trying to push like a semi-truck, okay, now is it heavy? Yes, but also what you're doing is you're fighting against friction. That weight is pushing down on that concrete, okay, and that friction is wanting to keep it still. It's going to resist your motion, okay, so if you're not strong enough, you're going to lose out to that frictional force. So it always opposes your motion. It's trying to go against it. So like right here, we have our applied force going to the right, and your frictional force is going the opposite way. Okay, so it's opposing that motion. So there are two types. You have one is your sliding. That is when you are actually moving. Okay, so so friction's there, it's just you have enough force to where you're overcoming that, but friction is still trying to slow you down. So that's sliding friction. And then two is if you have static. That means you did not overcome it. That means you were basically sitting still. Okay, so you are not moving. Okay, and the equation for that is FF equals mu. It's like a little U with like a little front tail thing times your normal force. That little mu, that little U right there is a coefficient of friction. And each material has a different coefficient. And normally we'd kind of give you those coefficients. Like if you looked at ice, ice would have a very low coefficient because you can slide across it a lot more easier. Okay, versus something like sandpaper would have a very high coefficient, which would want to keep you from moving. Okay, so frictional force is always opposing your motion. Then you have air resistance force, which is basically the same thing, except you're falling. So F air. Okay, that is a frictional force. Okay, that acts on an object through the air. So basically it means if you drop something, what's going to happen is it's not in contact with anything and it's not rolling on the ground, so there's no really friction there. Okay, but so you're going to have air resistance, okay, which is kind of like friction, there's just not a material there. So it opposes your motion as well. So think of like skydivers, so be thankful that there's air resistance, because when you pop your parachute, if there wasn't air resistance, it wouldn't do its job. Okay, so next one is called tensional force. That's like when you hang something. Okay, that is where it's transmitted. Now you could have multiple materials. We're just going to do some examples, like through a string, cable, or wire. You could say rope, chain, anything like that. There's plenty of things. Okay, when an object is pulled. Okay, so think of like you're hanging something from like a ceiling. Okay, there's going to be a tension force that's acting on whatever material you're using to hang that object from. And then last one is your spring force. Okay, so that is exerted by a compressed or stretched spring on an object. Okay, so the thing about when you have spring, when you stretch it out, it wants to return to normal. So think about like when you jump on trampolines, what you're doing is you're stretching out that spring and it wants to go back to normal. So it's going to launch you up. And you can also think of something like a Nerf gun where basically you're compressing a spring to be able to launch that dart. So that's that spring force there. So we're going to do a little basic free body diagram stuff. So show all forces acting on an object at one time. So doesn't mean there's going to be 7 of them. It just means we just need to show what's acting in that instance. Okay, it consists of arrows drawn from the object's center of gravity, which show the relative magnitude. What this means is when you have bigger arrows, that means it equals a bigger force. You don't have to like draw it to scale or anything, but if I have something that's accelerating, that's overcoming friction, my applied force should be a lot bigger than my frictional force. So we're going to show that here right now. So if I have an accelerating object, okay, so that means my F net does not equal 0 newtons. So that means it is not all balanced out. So we're just going to do we're just going to say we're pushing an object across the surface. So I'm pushing it to the right with an applied force. Okay, now what's acting on it is friction as well, but if I'm accelerating, that means I'm overcoming that frictional force. My applied force is stronger. So that FF is still there, it's just not as big. Now, if you're sitting on a surface, okay, FG is still going to be pulling down. Even if you're not sitting on a surface, FG is still going to be pulling you down. Now, if you're on a surface, okay, that surface is going to push back with the exact same force, so Fn. Now, literally 99.9% of the time, FG and Fn are always going to be equal the same. Otherwise, that thing would be going through the surface, which we're not going to worry about that. So this is what a basic accelerating object would look like because your applied force is overcoming your frictional force. So your acceleration would be considered positive in this case because you're speeding up in the right direction. Now, we're going to show what an object at rest or constant velocity is. So keyword there's constant velocity. It means you can be moving. If net force is 0, you can still be moving. It just means everything's nice and balanced out. So our F net is going to equal 0 newtons. So we're going to draw the same thing, same object. Okay, so I've got FG pulling it down. I've got Fn pushing it right back up. Okay, now my applied force is still going to be going to the right, but if this is a constant velocity or at rest, okay, that means my frictional force is going to be the same. That means that'd be like you trying to push an object that's too heavy. So you're applying a force, but that frictional force isn't letting you move it. Okay, so it's just sitting there. So that's what this would look like. Or you actually are strong enough to do it, but now you're just pushing it at a constant velocity. You're not accelerating, so you're not overcoming friction, and you're not decelerating, and friction is not overcoming you. Okay, so everything's nice and balanced out. So your acceleration here would be 0 meters per second squared. Now, last one, object slowing down due to friction. So we're going to draw this out. Okay, slowing down. That means frictional force is taking over. So that means I still have an applied force, but my frictional force is bigger. Okay, so it's overcoming that, and we still have FG pulling it down, and we still have Fn pulling it up. Okay, so my F net would not equal 0 because it is not balanced out, and my acceleration would actually be considered negative now because it's slowing you down in the opposite direction. Now, in the next video we're going to do is we're actually going to draw some of these. Okay, it's just important to know that you're not always going to have 4 of these going on. Okay, so just don't think that there's automatically an applied force, automatically a frictional force. Okay, you just take each one for its own thing and just kind of draw what you see there, which we'll do more in the next video.